Molecular orbital theory is added to valence bond theory to explain covalent bonding, and valence bond theory basically fails to explain some observed phenomena. And valence bond theory is mainly an explanation of what is already observed in bonding and does not really have any predictive power. Molecular orbital theory is more powerful in that manner, and it also explains one of the things observed, which is paramagnetism. Okay, paramagnetism is when a molecule is attracted to a magnetic field. And this will occur for either an atom or a molecule when there are unpaired electrons. So unpaired electrons cause something to be attracted to a magnetic field. All right, so let's compare some ions and atoms. O2 minus, neon, lithium, and we're going to actually do lithium plus, and carbon. So let's look at the electron configurations in a pictorial way and see if they have unpaired electrons. O2 minus has 6 electrons plus 2 more, so in the n equals 2 level, it completely fills the 2 n equals 2 level. And it has actually the same electron configuration as neon. Okay, so if we look at those two, they have, every electron is paired with another electron, so they are not paramagnetic. Look at lithium plus, it had, when it was neutral, it had 1 electron, the 2s, but when it was the ion, it lost that, so it has no unpaired electrons as well. Carbon has 4 electrons, and the 3rd and 4th go in 2 different p orbitals, so those two are unpaired. They don't have a downspin pair, so the carbon is a paramagnetic atom. All right, but molecules can be paramagnetic too, and that's kind of what we're more interested in now. So if you look experimentally, you'll find that oxygen is paramagnetic, and nitrogen is not. So we can try to explain that. If we try to explain that using valence bond theory, oxygen has this Lewis structure, and nitrogen has this Lewis structure. And we say that the oxygen has sp2 hybrids, 3 bonds each. Nitrogen has sp, and we say this one has 1 sigma and 1 pi, whereas this one has 1 sigma and 2 pi. Okay, but according to valence bond theory, all of them are paired, which does not explain why oxygen is paramagnetic, but we do know experimentally that it is. So let's look at molecular orbital theory. All right, we'll start with hydrogen, and we're going to start with 2 separate hydrogen atoms and form hydrogen molecule. So we have atomic hydrogen here and atomic hydrogen on this side, and we can show their electron configurations pictorially. They each have 1. Okay, you have 2 separate hydrogen atoms, each with 1 electron, and when they form the molecule H2, they form molecular orbitals, and they form, again, there's conservation orbitals, they form 1, which we call sigma bonding, and they form another one, which we call sigma star, which is anti-bonding orbital. So from the original, we form 2 more, 1 lower in energy, 1 higher in energy, and there's sigma bonding, we call them, and sigma star, anti-bonding. And then those 2 electrons will still follow the off-ball rule and fill in the lower level. And this is molecular hydrogen. Okay, and we can show the orbitals themselves. These are the hydrogen orbitals, okay, plain 1s orbitals. And then when you make H2, the lower one is something like this, filled in, and the upper one is one filled in and one not, and there is a node between them. Okay, so you form, so the bonding one allows the two electrons to fill the same space, whereas the antibonding one has a node between two lobes and the electron cannot be between. So this is the antibonding. And this one is the bonding. All right, and we can use those same orbitals to fill with other numbers of electrons. Okay, so let's look at the same two orbitals, okay, the sigma and the sigma star that are formed from these atomic orbitals. And for let's say we're combining, instead of hydrogen and hydrogen, we'll have a hydrogen and an H minus. Okay, and H minus would have an extra electron. And then we can place those three using the Aufbau principle. 1, 2, and 3. Okay, so in this case, we have 2 electrons in a bonding orbital like hydrogen, but we have 1 in an anti-bonding orbital. Let's do another example. Let's do helium dimer. Okay, we'll use the same orbitals, sigma and sigma star. And helium has 2 electrons. The other helium also has 2 electrons. So when they combine into the molecule that we're proposing, it would completely fill the antibonding orbital and the bonding orbital. Okay, and we can see how likely these are to form by looking at the bond order. And the bond order would be written as an equation, which is the number of bonding electrons minus the number of antibonding electrons and that whole thing divided by 2, because there's 2 electrons per bond. Okay, so we can evaluate these 2 above and see how likely they are. The number of bonding electrons in H2 minus are 2. The number of antibondings are 1. So 2 minus 1 is 1 divided by 2. So the bond order for H2 minus is 1/2. For helium, the number of bonding is 2. The number of antibonding is 2. 2 minus 2 is 0. 0 over 2 is 0. So the bond order is 0, which is why you don't find helium-2 in existence. And H2 minus, not so much either, but it's certainly more stable than helium-2. All right, then we can look at more complicated systems, row 2 or n equals 2 molecules like nitrogen, and we don't need to write the n equals 1 electrons because they're all completely filled when we're in this row. Okay, so we do the same thing. We'll have separate nitrogen atoms on each side and show their electrons and then combine them. So nitrogen has 5 electrons, 1, 2, 3, 4, 5, and the other nitrogen, when they're separated, has 5 electrons. And then we will bring them together and create the orbitals. The s orbitals will combine just like they did for the 1s orbitals that we did above, okay, into one sigma bonding and 1 sigma anti-bonding. Okay, so we'll make 1 here and 1 here. This is sigma and sigma star, but now we need to label which one they're from. They're from 2s. Because when we combine the p orbitals, we're going to make a total of 6 orbitals, and some are going to be sigma and some are going to be pi. All right, so for nitrogen, we end up with 2 pi's and a sigma, and then we have the same thing for antibonding. 2 pi's, it's pi star, and 1 sigma star. So the ones above are antibonding, and the ones below are bonding. So we have 3 bonding from the 2p, we have 3 bonding, 3 antibonding. From the 2s, we have a 1 bonding, 1 antibonding. And now we can put our electrons in. So the 2s electrons will completely fill both of the 2s sigma and sigma star orbitals. And then we have 6 electrons here. We fill using Hund's rule and Aufbau principle and the Pauli exclusion principle. There's 4, there's 5, there's 6. Okay, so we have all paired electrons, and we say this is diamagnetic. In other words, it's not attracted to a magnetic field because there are no unpaired electrons. Okay, now one thing to note is some of the second row elements will have a reversal of these 2 orbitals. The sigma 2p will be lower in energy than the pi 2p. Okay, so some elements reverse these 2. And one of those is oxygen. So we'll draw the oxygen molecular orbitals here. These 2 have been reversed. Okay, so this one is the sigma 2p, sigma star, oh, sorry, 2s, not 2p. They're for the 2s. And then down here we have sigma 2p, pi 2p, the pi's have 2, pi star 2p, and sigma 2p, sigma star 2p. Alright, so let's put in our electrons. The 2s electrons will completely fill these 2, just like they did in nitrogen. And now we have 4 on each side. We have a total of 8. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, guess what? Oxygen has unpaired electrons. That explains why it is paramagnetic. Unpaired electrons. So the molecular orbital theory does predict that oxygen would be paramagnetic. All right, and why don't you try filling the correct orbitals. For boron and carbon dimers, they have the same molecular orbital ordering that nitrogen does, and I've drawn these below. So use these diagrams, fill them up with the right number of electrons, and predict whether they would be paramagnetic or not. So suit for you. Okay, so boron. Each boron has 3 valence electrons, so that's a total of 6. So we'll start writing in our 6. 1, 2, 3, 4, 5, 6. We have unpaired electrons, so we would say that this is paramagnetic. And let's do carbon. Carbon has 4 valence electrons each, so 8 total. 1, 2, 3, 4, 5, 6, 7, 8. This has no unpaired electrons, so it would be not paramagnetic.